Okay, part A, we're asked to find the curl of f and use this to show f is conservative. So we have a theorem. Suppose we have a three-dimensional vector field, f of x, y, z, and it has component functions m, n, and p. Suppose these three component functions, m, n, and p, have continuous first partials in an open sphere or an open ball. Have continuous first partials in an open ball. Then we have a condition for conservative. F is conservative if and only if the curl of f is the zero vector for all points in the ball. So that's how we're going to show it conservative. Alright, so what is the curl of f? That's del cross f. We're going to use the three-dimensional differentiation operator. Alright, so let's see what this works out to be. We're going to use the cross product, so we're going to abuse notation all over the place here. I, J, K. And we're going to enter del in there. And we're going to enter the y, x plus z, y. So there's just abusive notation running rampant here. If we wipe out the row and column the I is in, we get the partial derivative of y with respect to y, which is 1, minus the partial derivative of this with respect to z, which is 1. So we get 1 minus 1. Wipe out the row and column the j is in. The partial derivative of y with respect to x is 0. The partial derivative of y with respect to z is 0. So we get a big old 0 there. And wipe out the row and column the k is in. We get 1 minus 1 there. And that simplifies to the 0. And as we stated before, since the curl is 0, and all these things have continuous first partials, we have that it's conservative. Okay. Our next one, B, is we're asked to find a potential for F. So remember what a potential is. What it means to be conservative is we need to find a scalar function F of 3 variables so that the vector field F is the gradient of the scalar function F. So in other words, remember what this means is the partial derivative of F with respect to X has to be the X component of the field F. So in this case, this is equal to Y. The partial derivative with respect to Y of the potential function has to match the y component of the field, and the partial derivative of the potential function with respect to z has to match the z component of the field. And so we're going to do our method of successive partial integrations and partial differentiations. So we can start with this first one and integrate with respect to x. And we're going to get our potential f, x, y, z. Integrate this with respect to x. You get x, y, plus a constant, which could depend on either y or z. Now at this point, we start taking partial derivatives and forcing it to match up with these things. So I can take a partial derivative of this with respect to y. So fy of x, y, z is what? Well, that's going to be x plus the derivative of this with respect to y. And what does this have to be equal to? I look over here, that's got to be equal to x plus z. So I get that the x's cancel out, and I get the partial derivative with respect to y of yz is equal to z, which means my c of yz is what? Well, I integrate this with respect to y. I get yz plus another constant, which in this case depends solely on z, because I've already taken care of the x and the y. So now I come down, and I know f of x, y, z is equal to xy plus c of yz. That's xy plus yz plus c of z. And so the last thing we need to do now is to match it up with the partial derivative with respect to z. So I'll go ahead and do that. If I can fit it all on one page here. The derivative with respect to z is 0 y plus c prime of z, and that's supposed to be equal to just y, and that gives us that c prime of z is equal to 0, which means that c of z is just a regular constant. So what's my grand final answer? F of x, y, z is xy plus yz plus a constant c. Okay, now it's important to remember that we can check this easily. How do we check that this really works? Well, let's take the gradient of little f and see that we get big F. So the gradient of little f is partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Oops. And we'll just see if this matches up with the field we're given. Derivative of this with respect to x, the only thing that survives there is going to be that y. Partial derivative with respect to y, x plus z. Partial derivative with respect to z is y, and sure enough, that is our original field f. That'll do it for quiz 18.